Hi everyone, this is part 3 of section 3, or the last part of chapter 3. In this part we have an example for tandem queuing network. So here we assume that we have two servers in series. So the arrival to the system is occurring at rate lambda. So we have a line, a queue for the first service, and the service time for the first service is assumed to be mu1, and then we have another queue for the service 2, and the service time for the service 2 is assumed to be mu2, and after that the entity or the customer will depart the system. Okay, so that's the system, and I think you had modeled this kind of system in your assignment, or also in the dump truck example. As you remember, after the loading station, the trucks will move to the scale, right? So yeah, I mean, there's nothing new in this example, so I'm not going to actually explain in more details because you know everything about this kind of system. Okay, so yeah, as you see here, we have 4 state variables because we have 2 servers, we have 2 lines, and we have 3 events here: arrival, departure from server 1, departure from server 2, and we can have also an end of simulation event as well if it's going to be ended by a certain time. So for the event, notice same as before, nothing new here. For activities, we have 3 activities here: interval time, server 1 service time, and server 2 service time. Okay, and for the delays, we have 2 wait times in Q1 and Q2, and that's it. For the logic of events for the arrival, at first we generate the next arrival at time t plus a, and then if the server is idle, then the server will take that arrival, so we need to schedule the departure event at time t plus s1 from server 1. And other than that, this new arrival will join the queue, right? For the departure from server 1, here we have again 2 things. At first, we need to check if there is some customers waiting in line. Then we will need to subtract 1 from the waiting line, and then that the customer will join the server. If not, the server becomes idle. And since it's departure from server 1, so it will be an arrival for the second server, right? So again, we need to check the status of the second server, and if it's idle, so this departure will join immediately the server 2 to have the service. Other than that, this departure will be actually added to the line of the server 2. Okay, so that's the logic, and we have here the flow logic for this event. For departure 2, D2, it's much simpler than the previous one because there is no server after this departure, and departure from D2 actually is departure from the system, and we just need to check the queue status. If there's some customers waiting in line, then server will serve them. Other than that, server becomes idle. Okay, and for the statistics, average customer wait time in a particular queue, or average customer wait time in the system, can be our performance measures here. Okay, so other examples in the queuing systems, we may have a server breakdown. Okay, so in this case, I mean, the number of servers being available to serve customers actually is changing over time, right? So in order to formulate this kind of system, we need to define an event for server going on breakdown or failure. Okay, and or queues with server vacation, and again, same as before, we need to have an event to start and end of server vacation. And queues with multiple types of customers, here customers are different, they're not the same. So in order to simulate this kind of systems, we need to define attributes to to customers, so customers will be individualized, will be differentiated by assigning attributes, and then we process the entities based on their attributes. Okay. Queues with the customer service priority. Preemptive repeat. This means that if we stop serving a customer in the middle of the service, then after getting back to work, that service will begin from the beginning, right? For example, waiter drops the food ordered by customer, so the chef prepares the entire food again. Okay. Or preemptive resume. This means that anytime that service of the customer is stopped, then it will be resumed from where it was stopped. For example, teller filling a customer form answers a call and then resumes the form filling process. Okay, or non-preemption. So in this case, once the service of a customer is started, it cannot be stopped. Okay. And or retrial queues with exponential retrial times. Here, if the system and the queue is full, the arrival won't leave the system. They may wait somewhere else. I mean, not in the system, but they will back again. They will back again to check if there is any room to join. So, for example, in restaurants, making restaurant reservation, for example. So if we have this kind of behavior for customers, we need to consider this behavior by its distribution in the system. Okay. And other examples to practice, it could be inventory model. We had this in our, I think, yeah, in online session examples. We had, I think, one or two examples for inventory models, and shipment consolidation model or maintenance systems, like a mixture of queuing and repair system. Okay, yeah, you can think about these systems as the systems that you may need to simulate the systems in terms of a discrete event simulation. Okay. List processing. This is a self-study slide here, so I'm not going to explain this in here. But if you are going to code your own program for a system, then you may need to study and learn this kind of stuff in order to use in your programming. But in this course, we assume that we are formulating the system and then we are implementing the system in Arena. So in that purpose, we don't need to know about this stuff. Okay. In summary, in chapter 3, we'll learn how to design a simulation model. So we learn the principles to formulate and model a system in terms of a discrete event simulation model. And we had different examples to discover how we can actually design a simulation model for different types of systems. Okay, so this chapter, beside chapter 2, is one of the most important chapters in our course because it deals with the design part of simulation. And I think the most challenging part of simulation is design. So I hope you have learned all details in these two chapters, and in the remaining chapters you will see that there is no design in the remaining chapters, and the remaining chapters are all about the statistics, that how we can infer the results obtained by the simulation. Okay. So we are done on chapter 3, and we'll have more examples in our live session this week. Okay. Thank you.